Welcome to Lecture 12, Section 3.5 of the Text Advanced Calculus Second Edition by Patrick M. Fitzpatrick, the Epsilon-Delta Criterion for Continuity. This is Dr. Gilbert, Eyabi. We defined the continuity of the function f from the domain D to the set of real numbers R at the point x0 in D in terms of convergent sequences in order to make precise the intuitive notion of if x is a point in D that is close to x0, then its image f of x is close to f of x0. Now, there is another way to capture this idea that is equivalent to the sequential convergence criterion, but which appears to be rather different. From the alternative perspective, certain properties of continuous functions can be seen more clearly. The alternative criterion for continuity is what is known as the Epsilon-Delta Criterion for continuity, and that is the subject of section 3.5. Now let's dive in. Subsection 3.5.1 definition. Let f be a function from D to the set of real numbers R. D is the domain. Then we say that f satisfies the Epsilon-Delta Criterion at the point x0 in the domain D, provided that for each positive number epsilon, there exists a positive number delta, such that for every x in D, absolute value of f of x minus f of x0 less than epsilon if the absolute value of x minus x0 is less than delta. Let's break that down. So to prove that a function f from a domain D to the set of real numbers R is continuous at the point x0 in D using the Epsilon-Delta Criterion, we proceed as follows. We suppose that epsilon greater than 0 is given. Our task is to find delta greater than 0. So what do? Step 3, we assume that the absolute value of x minus x0 is less than delta for every x in D, and then we verify that the absolute value of f of x minus f of x0 is less than epsilon for every x in D. So let's go back to the definition. For every epsilon greater than 0, there exists a delta greater than 0, such that for every x in D, whenever absolute value of x minus x0 is less than delta, we would have that the absolute value of f of x minus f of x0 is less than epsilon. We would look at a couple of examples to demonstrate this proof strategy. Note, in showing that the absolute value of f of x minus f of x0 is less than epsilon, we would most often make use of the difference of powers formula and the triangle inequality. So make sure you review some of the tools we looked at the beginning of this class. Example. Define the function f from the set of real numbers to the set of real numbers as f of x equals x cubed for every x in R. Prove using the Epsilon-Delta Criterion for continuity that our function f is continuous at the point x0 equals 2. Proof. We're going to use the proof strategy that we outline up here. We would suppose that epsilon greater than 0 is given. We would find a delta greater than 0. We would assume that the absolute value of x minus x0 is less than delta. And then we would verify that the absolute value of f of x minus f of x0 is less than epsilon for every x in D. And in this case, our x0 is 2. So let's go ahead and follow the procedure. Let epsilon greater than 0 be given. We must find a delta greater than 0 such that the absolute value of x minus 2 less than delta would imply that the absolute value of f of x minus f of 2 is less than epsilon for every x in our domain D, which in this case is a set of real numbers. This is how we proceed. We start off looking at the absolute value of f of x minus f of 2 and see if we can come up with a modified version that will permit us determine what our delta would be. Recall, we pick an epsilon greater than 0, arbitrary, and we find a delta. We have to find a delta. So the absolute value of f of x minus f of 2 equals the absolute value of x cubed minus 2 cubed. Difference of powers formula, x minus 2 into x squared plus 2x plus 4. Triangle inequality, that will be less than or equal to the absolute value of x minus 2 times all of this. Now recall that our x naught is 2. So for every x in the interval 1, 3, we are closing in on 2. This inequality is less than or equal to x minus 2, 3 squared, 2 times 3 plus 4, and that equals 19 times the absolute value of x minus 2, but that holds for every x in the open interval 1, 3. So go ahead and set your delta to be the minimum between 1 and epsilon over 19, or just go ahead and set your delta to be epsilon over 19. Again, epsilon greater than 0 is given. We have found a delta. In this case, our delta is epsilon over 19. Next, we are going to assume that the absolute value of x minus x naught is less than delta and verify this. So assume that the absolute value of x minus 2 is less than our given delta. Then the absolute value of f of x minus f of 2, which we got to be less than or equal to 19 times absolute value of x minus 2. So right here, less than or equal to 19 times absolute value of x minus 2. But x minus 2, the absolute value of all of that is less than delta. So this is less than 19 times delta, but our delta is epsilon over 19. So that is epsilon over 19, and the 19s will cancel out, and I end up with epsilon. In other words, I have just shown that given epsilon greater than 0, we have found a delta which equals epsilon over 19, and that is positive, such that whenever x minus 2, absolute value of all of that is less than delta, then absolute value of f of x minus f of 2 is less than epsilon, and that holds for every x in R. Therefore, we can conclude by the Epsilon-Delta Criterion that f is continuous at the point x naught equals 2. As a matter of fact, polynomial functions are continuous on R. So if I give you another example, say f of x equals 3x to the 5 plus 8x squared plus 9, and I want you to verify that f is continuous at the point 3, I expect you to use a very similar argument to come up with the conclusion. So that is the first level of application of the Epsilon-Delta Criterion for continuity at the point x naught. Another example. Define the function f from the domain R to the codomain R as follows. F of x equals negative x if x is less than or equal to 0, and x minus 1 if x is greater than 0. I want you to use the Epsilon-Delta Criterion for continuity to prove that the function f is not continuous at the point x naught equals 0. We already know how to do this using the sequential criterion for continuity. So we want to use the Epsilon-Delta Criterion for continuity. In other words, can we find an epsilon greater than 0 such that there is no delta greater than 0 that has the property that whenever absolute value of x minus x naught is less than delta, then the absolute value of f of x minus f of x naught is less than epsilon for every x in the domain D. If that is the case, then we would say that f does not satisfy the Epsilon-Delta Criterion for continuity, and therefore f is not continuous at the point x naught. Again, find an epsilon bigger than 0 and show that you cannot find a delta bigger than 0 that satisfies the property that whenever x minus x naught absolute value of that is less than delta, then absolute value of f of x minus f of x naught is less than epsilon. So proof. take our epsilon to be 1/2, and that is greater than 0. Then we conclude that there is no positive number delta that has the property that whenever the absolute value of x minus 0 is less than delta, then the absolute value of f of x minus f of 0 is less than 1/2. Observe that the absolute value of x minus 0 less than delta simply means negative delta less than x less than delta, and the absolute value of f of x minus f of 0 less than 1/2 simply means negative 1/2 is less than f of x, which is less than 1/2. According to the definition of our function, f of 0 would just be 0. And why is that the case? Since no matter what positive number delta is selected, there are positive numbers x in the interval negative delta delta such that f of x is less than negative 1/2. And we can look at that picture right here. So therefore, by the epsilon-delta criterion for continuity, we would conclude that f is not continuous at the point x0 equals 0. Subsection 3.5.2 theorem. Let f be a function from the domain D to the set of real numbers R, and let x0 be a point in its domain. Then the following are true. Number 1, the function f from D to R is continuous at the point x0 following the sequential criterion for continuity, i.e., f is continuous at x0 in D if whenever xn is a sequence in D such that xn converges to x0, then f of xn converges to f of x0. Call that plus. And the next assertion is that the epsilon-delta criterion at the point x0 holds. That is known as the epsilon-delta criterion for continuity, i.e., f is continuous at the point x0 in D if for every epsilon greater than 0, I can find a delta greater than 0 such that absolute value of x minus x0 less than delta implies absolute value of f of x minus f of x0 is less than epsilon for every x in D. Call that plus plus. Now you recall from discrete math, to prove that two assertions are equivalent, we have to prove that A implies B and B implies C. So let's go ahead and look at the proof. Proof 1 implies 2, or A implies B. Suppose that f from the domain D to the set of real numbers R is continuous at the point x0. We will argue by contradiction to verify that the epsilon-delta criterion at the point x0 equals D holds. Suppose, on the contrary, the epsilon-delta criterion does not hold. What we are saying is that there exists a certain epsilon naught greater than 0 such that if epsilon equals that particular epsilon naught, then there is no delta greater than 0 such that whenever the absolute value of x minus x0 is less than delta, we would have that the absolute value of f of x minus f of x0 is less than epsilon. Let's go back to our statements. Plus plus is the epsilon-delta criterion. Plus is the sequential criterion. So let n be a natural number. Then plus plus does not hold for epsilon equals epsilon naught and delta equals 1 over n. Recall, we did say that there is a particular epsilon naught that is positive, such that if I set my epsilon to be that epsilon naught, then there is no delta bigger than 0 that would cause this chain of inequalities to hold. Okay, so if my epsilon is epsilon naught and my delta is 1 over n, plus plus does not hold. But what does that mean? This means precisely that for every natural number n, there exists an x in D such that the absolute value of x minus x0 is less than 1 over n, but the absolute value of f of x minus f of x0 is greater than or equal to epsilon naught. Choose such a point and label it xn. This defines a sequence xn in D that converges to f of x0. This clearly contradicts the assertion that the absolute value of f of xn minus f of x naught is greater than or equal to epsilon for every n in n. Thus, by this contradiction, we can conclude that the epsilon delta criterion at the point x naught in D holds. So that is 1 implies 2, or A implies B. Now let's go ahead and look at the reverse. B implies A. Assume that the epsilon delta criterion at the point x naught in D holds. We would show that f from D to R is continuous at x naught in D. RA we would verify plus the sequential criterion for continuity. And what does that say? Suppose xn is a sequence in D such that xn converges to x naught. We have to show that the sequence f of xn converges to f of x naught. All we have to do here is let epsilon greater than 0 be given, and we find a natural number n such that the absolute value of f of xn minus f of x naught is less than epsilon for every n greater than or equal to n. Recall the epsilon n definition of convergence back in chapter 2. So that is what we are using here. Now, by the epsilon delta criterion at the point x naught in D, we can select a positive number delta. Recall, we are already given that epsilon is greater than 0. So by the epsilon delta criterion, we can select a positive number delta such that whenever the absolute value of x minus x naught is less than delta, we can always conclude that the absolute value of f of x minus f of x naught is less than epsilon. Moreover, since xn converges to x naught, we can choose n in n such that this inequality here holds, but x is replaced with xn. So we can choose n in n such that the absolute value of xn minus x naught is less than delta for every n greater than or equal to big N. And that works because delta is greater than 0, and we're using the epsilon n definition, or you can call it the delta n definition in this case. Now look at 1 and look at 2. This is what we have from the epsilon delta criterion for continuity at the point x naught. This is what we have from the fact that xn converges to x naught and delta is greater than 0. Putting 1 and 2 together, we can conclude that for every epsilon greater than 0, there exists a natural number n such that the absolute value of f of xn minus f of x naught is less than epsilon for every n in n. Again, what does that mean? It simply means that f from the domain D to the set of real numbers R is continuous at the point x naught in D, following the sequential criterion for continuity, and that proves the theorem. In other words, we're saying that the sequential criterion for continuity is equivalent to the epsilon delta criterion for continuity. Now let's proceed. In section 3.4, we introduced the concept of uniform continuity. Now that we have moved on from the sequential criterion for continuity to the epsilon delta criterion for continuity, it only makes sense that we introduce an equivalent concept for uniform continuity. And that is where definition 3.5.3 comes in. A function f from D to R is said to satisfy the epsilon delta criterion for continuity on the entire domain D, provided that for every epsilon greater than 0, there exists a positive number delta, such that for every uv in D, whenever the absolute value of u minus v is less than delta, we would have that the absolute value of f of u minus f of v is less than epsilon. We would call this the epsilon delta criterion for uniform continuity. A restatement of the epsilon delta criterion goes as follows. F from D to R satisfies the epsilon delta criterion for continuity on the domain D, or for uniform continuity, if for every epsilon greater than 0, there exists a delta greater than 0 such that for every two numbers u, v in D, the absolute value of u minus v less than delta implies the absolute value of f of u minus f of v is less than epsilon. Let's go ahead and test that with an example. Example, define the function f from the domain, which is a closed bounded interval 0, 20, to the set of real numbers r by f of x equals x cubed. Prove using the Epsilon-Delta Criterion that f is uniformly continuous on the domain D, the closed bounded interval 0, 20. Proof. We're going to follow the exact same strategy we used to prove the Epsilon-Delta Criterion for continuity. Let epsilon greater than 0 be given. We find delta greater than 0 such that whenever this inequality holds, then this inequality would also hold. We start off with this inequality so we can have an idea on how to define our delta. Absolute value of f of u minus f of v is the same as the absolute value of u cubed minus v cubed. Applying the difference of powers formula, we have absolute value of u minus v times u squared plus uv plus v squared. Again, if you have forgotten some of this, you may have to go back to chapter 1 and review some of the tools of analysis that we presented at the start of this class. So, by properties of absolute value, this is the same as the absolute value of u minus v times the absolute value of u squared plus uv plus v squared. And by the triangle inequality, that is less than or equal to all of this. And since x is from the closed bounded interval 0, 20, the highest x can be is 20. So this quantity right here is less than or equal to the absolute value of u minus v, and replace u and v by 20. And we end up with 1200 times u minus v. We set our delta to be epsilon divided by 1200. Epsilon is greater than 0. 1200 is greater than 0, so delta is greater than 0. Now assume that the absolute value of u minus v is less than delta. Then the absolute value of f of u minus f of v, which we already know is less than or equal to 1200 times absolute value of u minus v, right here, would be strictly less than 1200 times. We had assumed that the absolute value of u minus v was less than delta, and delta is epsilon over 1200. So this is less than 1200 times epsilon over 1200, which equals epsilon for every uv in D. What is the conclusion? By the Epsilon-Delta Criterion for continuity on an entire domain, we can conclude that f is uniformly continuous on the closed bounded interval 0, 20. And that brings us to the end of that example. Now, recall how we did prove that the sequential criterion for continuity at the point x0 was equivalent to the Epsilon-Delta Criterion for continuity at the point x0. What do you think would happen with uniform continuity? Well, the same story. Subsection 3.5.4 Theorem. If f is a function from a domain D to the set of real numbers, then the following two assertions are equivalent. Number one, f is uniformly continuous following the sequential criterion for continuity, i.e., whenever un and vn are sequences in D such that the difference of the sequences converges to 0, then the difference of their function values would also converge to 0. Statement 2. The function f from D to R satisfies the Epsilon-Delta Criterion on the domain D that is known as the Epsilon-Delta Criterion for uniform continuity, i.e. for every epsilon greater than 0, there is a delta greater than 0 such that for every uv in D, absolute value of u minus v less than delta implies the absolute value of f of u minus f of v is less than epsilon. The two assertions are equivalent. That means we're going to prove that C implies D and D implies C. Good news. The proof is entirely similar to the proof of Theorem 3.5.2, and therefore I would leave that as a sieves. Simple exercise for serious students. And that brings us to the end of section 3.5, the Epsilon-Delta Criterion for continuity and the Epsilon-Delta Criterion for uniform continuity. And I will see you next with section 3.7, limits. I'm going to skip section 3.6 and I'll leave that for advanced calculus 2. Thank you very much. God bless you.